This is part 2 of the Taylor series and Maclaurin series. Now let's recall in example 2 here. We have come up with a series, so that series right here. We call it the Maclaurin series in this case because it centers at 0. We come up with the Maclaurin series that um, equivalent to these functions. Now I'm going to want to show you why it's important we do that. Um, First, when we use approximation, so let's say if you want to find the values, anything that you're dealing with cosine, we can use the right hand side to do that. But the right hand side is a series. And so that's why we have the concept of Maclaurin polynomial or Taylor polynomial. It's just because we cannot use all the terms. So we have to truncate it somehow, and we have to determine how many terms we need or what's the degree of the polynomial we use to approximate that. So with that said, if you do homework, you're going to see the problem will ask you to, let's say, find a Taylor polynomial for this function, so right, cosine x. Now this time we want a Taylor polynomial. And when we take the polynomial, we often have to determine what's the degree. Sometimes we say the term, the number of terms. So let's say we want degree 4. Then what it means is, I think the notation is P4. Okay. So what it means is we're going to use this Maclaurin series. We only stop at the 4th degree. So it will be 1 minus x squared over 2 factorial, and then plus x to the 4th over 4 factorial. So what we say essentially is the 4th degree polynomial here, we can use it to approximate this function cosine. Okay, so cosine of x is about the same as 1 minus x squared. If you simplify, it's really 2, and then the 4 factorial is really 24. So approximate. Okay, and then what if you can try and see if we want to find what is cosine of 0.12, right? Then instead of if you do cosine of 1.12, I can plug in and say, well, that's approximately 0.12 squared over 2 plus 0.12 to the 4th over 24, right? Then you do this math on calculator, right? So that could be very easy to do. Okay. And here come the application, or why we do this. You imagine if we asked to do the cosine of 0.12. Okay. Now, of course, we would plug this in calculators and then spit out the answer. But the question is, how does the calculator figure out cosine of 0.12? Right? So if I give you a cosine, even though special value is pi4, right? So that one we know the answer is cosine pi half is easy, cosine pi4. But then when we do the cosine of special values, what we do is we draw the unit circle, and then right, so here's in 45 degrees, and we're kind of looking at the x coordinate at this point, and I think it's root 2, right? So trick, that's what we learned. But the problem is, how do we implement this knowledge or whatever we do here into the calculators and calculate that and give us the answers for 2 or 2. You see, calculators, the programmer, when they write the program to do this, they cannot do this. I mean, they just cannot basically ask them to draw an angle, then do all these things. So it can't. So in terms of implementing the algorithms or a way, we teach the computer or calculator to do the complex operations. Okay, we have to come up with a way to do it, and he is one way, not all the time, but this is one way. Is if you want to do cosine of pi fourth, what we would do instead is we do this formula in calculator or computer. Okay, let's take 1 minus then pi over 4 square over 2 divided by 2 plus pi over 4 to the 4 divided by 24. See, these are simple operations we can actually write to make the computer do that, right? So that's the way we do. Okay, and then by the way, I will spend quite some time in this second video to go about the applications in why we are doing all the Maclaurin series or the testing series, etc. So I'm going to spend this whole video over the motivations and applications. If you don't have time or you are not quite interested in, you can skip this video, or let's skip it for the rest of the video here. You move on the third video and go more about the examples and what you need to do in homework. Okay, so these are more like motivation and application. Or other things we could do is when it's come to solving equations, right? Solving equations. So when he's, we call this an example 1, right? So that's one type of example you evaluate. Or when you have the next example, if I want you to solve, hey, can you solve this equation? It's cosine of x equal, let's say, subtract 3x equals 0. See, different look simple, right? But the thing is, this is trick. There's a linear function pi. I mean, how can you solve this equation for x? Again, it's difficult. But then, if you use approximations, and we could say with 4 degree, it doesn't have to be 4 degree. If you want, again, it depends on the accuracy. You could actually do it with more. So let's say if you want to be more accurate in terms of approximations, we can choose P10. Then essentially P10 is this one. As I go from P all the way to here, stop. That's P10. X, right? So that's 10 degree. So that's more term, right? So if you use cosine of x, then you replace that with the polynomial, right? X squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial and minus x to the 10 over 10 factorial minus 3x equals 0. Now, I'm going to use a P10 here, right, instead of cosine. See, then we have the new equations, and now this equation is much easier to solve, and this is polynomial. It's a 10 degree, and we do have a way to solve, although you probably don't know, but polynomial with degree 10, it's way much easier to solve, and it's doable. Okay. Another applications. Think about derivative and calculus, and we'll do this later since we don't have enough theory to talk about. But what I'm trying to say is, if you are asked to say do the integrations, okay, if you do the integrations, something might be a bit more complicated, say x times cosine x dx. Actually, this one we have a way to do it. We call this polynomial times cosine, right? So we can use integration by part. Yes. Now I could make the example much harder, but as you can see, the cosine of x is actually hard. Okay, when it comes to the trig functions here. Well, maybe you can throw in, I can throw in something that's hard. Maybe integration by part cannot be done. We do root x. Yeah, we put root x and we have trouble. So how do we integrate this? Again, if you use approximations, cosine is the same as that one, then I could replace cosine. This time we use this one, right? So it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th times 6 factorial. I'm going to use 6 p6 this time. All right, so let's stop right there. Dx. Okay, can you integrate that? Yes, why not? Because this is the x to the half power. I can multiply it in and then get rid of my multiplications here. See, this is the problem is multiplications there. Multiply it in, that'll be x to the half times 1, and then time here, it'll be x to the 2 1/2, so it'll be 5/2 over 2 factorial plus x to the 4 1/2 or 9/2 over 4 factorial minus x to the 13/2 over 6 factorial dx. And you can see I don't have problem integrating this because these are just the power of x with separate terms. I can integrate it term by term, add 1 to this x to the 3/2 divided by 3/2 or times 2/3, and he's minus x to the, that's 7/2 over 2 factorial divided by 7/2 or times 2 7, and so on. Right, so x to the, well, that's 9/2 plus 1 is 11/2 over 4 factorial times 2 over 11, and minus x to the 15/2 over 6 factorial 2 over 15. You see, we make things much easier to do with when we use polynomial, or we call Taylor polynomial, to approximate a function. Okay, so that's the whole point of doing all of these. Okay, finding the series representations for a function. So instead of dealing with function, we're dealing with a polynomial. Another thing we need to watch out is when it comes to the series. Okay, it's a series like this. Then don't forget that the series not always converge. Not all converge, right? So sometimes it converges and sometimes it diverges. So that's why in the previous section we learned the interval convergence. So that means the series over here, when you look at the series over here, it might converge on an interval, like from 2, -2 to 2, -3 to 3. But you look at this example here, actually it converges from -infinity to positive infinity in this case. So that means they always equal for every values of x. Sometimes when we have a series and this function, if you look at the both sides, they're not always the same because on the right side, sometimes it diverges. In other words, when you plug in, you got infinity. You got infinity. Okay, so he's second alternate series on the right, so it converges. But sometimes it diverges and converges some on from -3 to 3. Then this equality only hold on this particular interval. Okay, so again, now we kind of put everything together. We want to find series that represent the functions. On a series, we want to know the interval convergence. That means the interval on which the right-hand side equal the left-hand side. Okay, I think that's the importance of knowing the interval convergence, of finding the Taylor series or the Taylor polynomial that will approximate this function. All right. Now, we look into the next example. We actually take advantage of this formula. Right, so you see here, I'm taking advantage of this one. When you have square root of x cosine x, you just take root x here, multiply, you got a new series, right? New polynomial. Essentially, we would do the same. It's like building from cosine of x. If I ask you to find what is the, can you find a series, the Maclaurin series for cosine of 2x? Okay, cosine of 2x. Then we're going to use this. See the cosine of x, right, is 1, that's 1 from above. Then cosine of 2x, you just replace x with 2x, 2x, 2x. Now you got a new series, right? Then we got a new series. Okay. And again, if you want to figure out anything relating to the cosine, we're going to use this formula. All right. I think that is part 2, and then I'll continue to do more example in the next video.